Okay. So we'll start with the next phenomenon that is called as refraction of light. So write it down. Refraction of light. Okay. See, till now we discussed about a concept called as reflection. So what happens when the light is hitting a particular smooth and a shiny surface, it bounces back, making certain angles which are same. The angle of incidence is equal to the angle of reflection, something like this. All these things it is going to make. Now the question is, if we have a boundary like this, where this side of the boundary is transparent. Okay, what do you mean by transparent? Means you can see through it, right? You can see through it. Then, if the light is hitting this particular surface, what will happen when it passes through the other side? The question is it going to get bounced back, or will it be able to pass through the other surface as well? Will it be able to move like this? This is the next question. So what do you think will happen? Sorry?
Sir, it will pass in the other direction. It will pass through.
It will actually pass. That's right. So whenever you have a transparent medium, it is going to pass through. See, for example, you have your window, right? You have a room where there is a window, right? And the window is made up of a transparent material. The light from outside is going to enter inside, right? Because it's a transparent surface. But the question is, when it is entering, is the light going to follow the same path in which it was traveling, or is it going to get deviated is a question. Okay, what do I mean by it will get deviated? Means there will be a slight bending of light that is going to take place. Means if I take this as the incident ray, then this will be the actual path. This will be the actual path in which the light rays are going to travel. Okay. Now, if there is a phenomenon where the light starts bending towards or away from the normal, is what we call it as refraction of light. So basically, refraction is nothing but the bending of light when it is traveling from one medium to another. So the best example is something like this, guys. So they have given, see, let me read out. If you go to, you have to observe all these things. You might have observed that the bottom of a tank or a pond containing water appears to be raised. Have you ever observed this? If suppose you have a tank, okay, you have water tank, or you go to a pond. When you try to look at the bottom, if at all you're able to see the bottom, for example, your water tank is there, right? If you're able to see at bottom from the top, you can see that it is slightly raised. And why is it happening? Because of this particular phenomenon. Similarly, when you have a thick glass slab which is placed over a printed matter, the letters appear raised. See, have you ever done this, guys? You take a plastic scale and you try to look at the tube light. Have you ever done this?
Yes.
Yes, sir.
So what is it you observe?
So white light will be spreading in different lights.
You will get different colors, right? Actually, those different colors are coming out because the white light is getting bent at different angles. So white light actually comprises of 7 colors. Vibgyor, you would have already known this. So those 7 colors it is comprised of are actually, you're able to see them as individual component because of this bending of this light. Okay. So that is a best example for a phenomenon called as refraction. Okay. Similarly, if you take a pencil, okay, if you take a pencil and you partially immerse it in water in a glass tumbler, then when you see it from the side, it will appear as if the pencil is bent, but actually it would have not got bent. And why is it happening? It is because of the principle of refraction. So keeping all these activities in mind, if the question is asked about what does refraction mean, what are you going to tell me? So write down the definition for it, guys. It is a phenomenon means something which you can see. Bending of light when it travels from one medium to another. Okay. So refraction means bending of light, the phenomenon of bending of light when it travels from one medium to another. Okay. See, now I'm going to concentrate on some important terms I want everybody to observe. In your textbook, they would have explained everything based on activity. Since we cannot do an activity and see now, I'll try to go a little bit mathematical so that it helps you for the problems as well. Okay. So refraction of light. So definition is over.
Sir, excuse me, sir. Excuse me, sir.
Students, I'm sorry, I didn't know that the connection got cut. So till which point was I audible?
So you have just started.
I just started. I didn't get you.
Sir, you just started law of refraction, sir. You just wrote it.
I just wrote law of, I taught so much. I'm sorry, I didn't know that the connection got lost. So after law of refraction, actually what I did is I cancelled it and I wrote, I was explaining about medium. See, I was trying to tell you this concept. So if you observe the technical word that I was concentrating in, when I talk about refraction of light, I
Excuse
told
me,
that
sir. Sir,
Tell me, ma.
sir, could you please repeat from the definition?
Yeah, I'm doing it. So phenomenon of bending of light when it travels from one medium to another, right? So this is what is called as refraction of light. So here, if you observe, the technical term that I was concentrating upon is one medium to another, right? So here, the word we need to concentrate is medium. So I was telling about medium. What is medium? Medium is basically the region in which the light is traveling, except suppose you talk about light traveling in air. That air is called as medium. Light traveling in water. Water is the region in which the light is traveling. So water is a medium. So basically, medium on a comparative scale. Okay, singular is medium, the plural is media. Okay, plural is media. Basically, medium is classified into two types. What are they? One is called as rarer medium and denser medium. Okay, I hope it is clear till this point. Now, if I talk about the speed of light in vacuum, so what is the speed of light in vacuum? It is going to be 3 into 10 power 8 meters per second. Right, this I would have discussed in the first class. And this is the maximum possible speed of light which it can travel with. It is not possible for you to generate speed greater than this. Okay. Now, if I have a boundary, please stop me if there is any point that is not clear. Okay. So if there is a boundary which is separating two media, M1 and M2. Okay. Let's say the speed of the light in the first medium is V1 and the speed of the light in the second medium, I call it as V2. If on a comparative basis of speed of light in both the media, if the speed of light in medium 1, if the speed of light in medium 1 is greater than the speed of light in medium 2, then medium 1 can be called as the rarer medium. That is what I'm trying to say. Are you able to understand? So on a comparative basis, if the speed of light in medium 1 is greater than the medium 2, then medium 1 is called as the rarer medium. Obviously, the vice versa is going to be the denser medium. So from all these definitions, the conclusion that we can make is speed of light in rarer medium is always greater than the speed of light in denser medium. Okay. Now listen to this carefully. Suppose they give you a question like the speed of light in a given medium is 2.2 into 10 power 8 meter per second. And the speed of light is 2.5 into 10 power 8 meter per second. Obviously, which one is going to be rarer and which one is denser? So which one is rarer and which one is denser, guys? First, second. You people tell me.
Sir, second one will be rarer and first one will be.
And this, very good. This is called as rarer medium, this is denser medium. So when a higher order thinking skill based question is given, every time they will not say that this is rarer and this is denser. They expect you to know it. Okay. So for that, how are you going to know the definition? Only by looking at the speed of lights. Okay. So you guys are clear with this concept. Next. So based on this, I'm going to give you another thing that is called as the laws of refraction. Okay, write down the heading as the laws of refraction. Now the question is, let's recollect what are laws of reflection. So what did the laws of reflection speak about? They spoke about the angle of incidence, angle of reflection, and the normal. In a similar way, secondly, it also spoke about the incident ray, reflected ray, and the normal. Right? Now, here it is going to speak something similar only. Here also, incident ray. Can you guys guess? Incident ray, refracted ray, and normal all lie in the same plane. Accepted? Incident ray, refracted ray, and normal all lie in the same plane. Second, okay, ratio, here it is slightly different. Concentrate, guys. Ratio of sine of angle of incidence to the sine of angle of refraction is a constant named as refractive index. Is a constant which is named as refractive index, and the symbol used for refractive index is like this. You'll put a line like this and a U. It is generally pronounced as mu, which is called as mu, because it's a combination of m and u. And mu is moreover, it's a Greek letter. Okay. This is a very, very important point. Please make a note of it. Okay. The ratio of sine of angle of incidence to the sine of angle of refraction is always a constant. And the constant is named as refractive index. Okay. Did you guys learn trigonometry? In your school, are they teaching?
No, sir.
No, sir.
Okay, no issue. As of now, except there is something called as sine. Okay. So I is called as the angle of incidence. If you write SIN, you will not write SINE always. SINE is a full form, SIN is a short form. I don't know why that E is alone removed. Okay, SIN divided by sine of R is equal to mu. And this is called as Snell's law. Okay. This law is called as Snell's law. Well, Snell is the name of a scientist. Okay. Am I clear? Shall I proceed?
Yes, sir.
Okay. Now I'm going to define refractive index. Now we need to know the definition of refractive index. Okay. Write down the definition. It is defined as the ratio of speed of light in vacuum to the speed of light in a given medium. Okay, so it is defined as the ratio of speed of light in vacuum to the speed of light in a given medium. So mu is written like this. Speed of light in vacuum to speed of light in medium. There is another important definition, okay? It has no units. Shall I proceed? Mu value is always greater than 1 also. Make a note of this point. Reason being, the numerator is having speed of light in vacuum. I already told you, speed of light in vacuum is the most. That is 3 into 10 power 8. Speed of light in any other medium compared to vacuum is going to be less. Hence, mu value is always greater than 1. Okay.
Yes,
Sir,
sir.
can you repeat the reason why it is greater than 1?
Ah. Because speed of light in vacuum is how much? It is 3 into 10 power 8 divided by. If you take the speed of light in any other medium, it is always less than 3 into 10 power 8. So if the numerator is greater than the denominator, the ratio is always greater than 1.
Okay,
Am I
sir.
clear?
Yes, sir, I got it.
Please make a note of that point.
Yes, sir.
Yeah. Okay. Now I'll proceed. Now listen to this, guys. Refractive index of rarer medium versus refractive index of denser medium. Okay. So let's say mu r is refractive index of rarer medium. Okay. This will be speed of light divided by speed of light in vacuum divided by speed of light in rarer medium. Guys, does that make sense? Rarer medium. Similarly, mu d is a refractive index of denser. What is it going to be? Speed of light
So speed
in
of light in vacuum divided by speed of light in denser medium.
Very good. Light in denser medium. Now, if I divide mu r with mu d, what will I get? I will get speed of light in denser by speed of light in rarer. Did you guys understand why I got that? Because if I take this as A by B and this as C by D, A by B divided by C by D will be actually A by B and this is A by D. Why I wrote A is because this is also speed of light in vacuum, this is also speed of light in vacuum. This and this will get cancelled, I'll get D divided by B. D is nothing but this thing and B is nothing but this thing. That is why I wrote speed of light in denser divided by the speed of light in rarer. I hope this step is clear. Everybody.
Yes, sir.
Very good. Now, I have an important question to ask. We know that speed of light in denser is less than speed of light in rarer. This is accepted. So this is according to the definition, nothing that we have found. So mu r divided by mu d will be equal to speed of light in denser, that is the numerator is less than the denominator. So when numerator is less than the denominator, what will happen? You will get the fractional value less than 1?
Yes, sir.
Means if you divide a refractive index of rarer and refractive index of denser, the final output will be less than 1. From this, we can conclude that mu r is always less than mu d. Okay, so this is where the confusion starts. I want you people to be careful. Speed of light and rarer is greater than the speed of light and denser. Whereas when you talk about refractive index, it is just the reverse. Okay, clear, guys? Now, so suppose you have a question where they say the refractive index of a particular medium is 2/3 and refractive index of another medium is 3/4. Now, which one will you call it as rarer and which one will you call it as denser? Tell me. So mu2 will be,
Sir, mu1 will be rarer and mu2 will be denser.
very good.
Sir, can you explain this once more? I got disconnected.
Which one?
Sir,
Your voice is breaking. Hello, your voice is still breaking. I'm not able to hear you. Am I audible?
Yes, sir.
Okay. So I just gave a conclusion. The speed of light in denser medium is less than the speed of light in rarer. That's it. Okay. So having these points in mind, I'm going to find out how the light is going to bend. So one thing we are clear that when the light is traveling from one medium to another, okay, this is first medium, this is the incident ray, this is the angle of incidence. Okay, and this is going to be the actual path. Right now, the question is, when we say bending of light is going to take place, in which direction is it going to bend? Is it going to bend towards the normal or away from the normal? That's what we are going to find now. Okay. Now, light traveling from rarer to denser. See, all the logic that I'm going to explain now will not be there in the textbook. So concentrate, guys. Suppose if I call this as the rarer medium, if I call this as the denser medium, then mu1, mu2. What is the relation between mu1 and mu2? Mu1 is less than mu2. First point to be noted. Let me call this as equation number 1. Okay. Now, what is Snell's law telling? Please revisit and tell me. Snell's law says sine of angle of incidence to the sine of angle of refraction is equal to mu. That is what it told, no? But the more generic formula is it is equal to mu2 divided by mu1. Guys, I'll tell you a relation. I'll tell you how to remember this. Okay, concentrate. You have refractive index in a medium, right? So this is the boundary. This is the first medium, second medium. So refractive index of a medium multiplied with sine of the angle in that medium, that is sine I, is equal to refractive index in the second medium into sine of the angle in the other medium, which I call it as R, where I stands for angle of incidence and R stands for angle of refraction. Did you guys understand what I told? Okay. So
Yes, sir.
if you rearrange this equation, you will get sin I by sin R is equal to, you will get sin I by sin R is equal to mu2 divided by mu1. Okay, means sine and the refractive indices are actually inversely proportional to each other. I is in medium 1, R is in medium 2. Okay. So now observe, sin I by sin R is equal to, what can you say about mu2 by mu1? From this you can say mu2 by mu1, is it greater than 1? Guys, are you able to understand why is it greater than 1? Because refractive index of denser is greater than the refractive index of the rarer. If there is any doubt, please stop me, okay? All these are slightly technical. Concentrate. So, since sin I by sin R, listen. Since sin I by sin R is equal to mu2 by mu1, but mu2 by mu1 is greater than 1, can I say sin I by sin R is also greater than 1? Which implies I will be greater than R. This is a very, very, very important relation. So what I'm trying to say is angle of incidence will be greater than the angle of refraction. Meaning, if you take a line like this, okay, if this is the incident ray, if you drop a normal at this point, if this is taken as the angle of incidence, then what is this? This is called as the actual path. No. If this angle is I, tell me how much is this angle, guys?
I.
Why is it so? Because they are vertically
Vertically
opposite.
opposite angle.
Yes. But when the light is traveling from rarer to denser, what is going to happen, guys? They told that the angle of incidence is greater than the angle of refraction. Means the light will no more be able to travel in the actual path, but it will start bending like this. Okay. Since it is bending in this form, this angle is what is R and this angle is I. Are you able to understand that I is greater than R? Let's say if I is going to be 60 degrees, R is definitely going to be less than 60 degrees. So the conclusion that we are going to make from here is, when light is traveling from rarer to denser medium, is it bending towards the normal or away from the normal?
Towards the normal.
Light bends towards the normal. 200% sure that this mathematical reason is not there in the textbook. But I explained it for your understanding because I've seen many of them mugging it up without knowing the reason. But I don't want you to be like that. Okay? If somebody asks you, now you know, have a better reason. Why is it happening? It is because of the refractive indices. Right? So light bends towards the normal. Right? Now, shall I proceed, guys? What happens when light is traveling from denser to rarer? What is going to happen? Now let's see how much you guys have understood Snell's law. So let's say this is the incident ray. If I take this as the angle of incidence, then this is going to be the actual path. No doubt in that. No doubt in that. Now comes another important question. Listen. If this is mu1 and this is mu2, now tell me which medium is denser and which medium is rarer.
So mu1 is denser and mu2 is rarer.
Yes, this is denser, this is rarer. So I can blindly say mu1 is greater than mu2, which implies mu2 by mu1 is how much? Smaller number divided with a bigger number. Is it going to be less than 1 or greater than 1?
Less than 1.
Yes, less than 1. So there is a number which is less than 1. So next, applying Snell's law at P. So when you apply Snell's law at P, what are you going to get? I told you a method already. So what is it? Refractive index of a medium into right sine of angle in that medium is equal to, what should I write on the right hand side? Correct it. So complete it. Mu1 into sine I is equal to mu2 into sine R. So sine I divided by sine R is still going to be mu2 divided by mu1. But this time mu2 divided by mu1 is less than 1, which implies I is less than R. So what is that you guys are able to understand? So that the light will no more be able to travel in its actual path. Rather, if this is taken as I, then it should travel at an angle which is greater than I. So it will start moving like this. And this angle is what is going to be R. So what are the important conclusion we can make? Denser to rarer medium. What happens? Light
The light
bends
bends away from the normal.
away from the normal. Okay. So by now you guys would have understood what is towards and what is away. Right? Shall I proceed? I hope everybody has made a note of these points. Right, right.
Yes, sir.
Yes, sir.
I'll proceed to the next concept. That is, I'm going to talk about the application of this. Okay. The refraction of light through a glass prism. Sorry, through a glass slab. To be more specific, I can call it as a rectangular glass slab. So refraction of light through a rectangular glass slab is what we are going to see. So you guys would have seen these paperweights, no, glass paperweights. If you take the paperweight made in the shape of a cube, cuboid, the paperweight is made in the shape of a cuboid, then the cuboid is what we call it as a glass slab. Okay, so let's say there is a glass slab like this. let's say there is a glass slab in this way, and when light is hitting this surface, so what is this called as the incident ray, right? So always at the point of incidence, our job is to draw the normal. This is I. Okay. Now, this is air medium, and this is obviously glass medium, and outside it is again air medium. Remember, air is rarer medium, and glass is denser medium. Okay. So when light is traveling from air to glass, what is happening?
Sir, the light will bend towards the normal, sir.
That's right. So for us to understand what is towards the normal, we first need to draw the actual ray, right? So from the actual ray, we will take the light bending towards the normal, means there is a clockwise turn, right? So this is going to be the angle of refraction. So I hope by now you would have understood that angle of refraction is nothing but angle between the refracted ray. Refracted means bent ray and the normal, right? So this is the second point of incidence. Now at the second point of incidence, we are supposed to draw a normal. Okay. This is going to be the actual path. This is going to be the actual path. So if this is R, if I drop a perpendicular here, there's 90 minus R. So this will be R, alternate interior angles. So if this is R, how much is this angle? This is also R. Right? Now, when the light is traveling from denser to rarer medium, what is going to happen? It will start bending away from the normal. Correct? So this ray is called as the emergent ray. What is it called? It's called as the emergent ray. Okay. So when this is called as the emergent ray, this angle is called as the angle of emergence. Any doubt till this step? It's called as the angle of emergence. Any doubt till this step, guys?
No, sir.
Okay. Now, there are 2 points of instance, P and Q. If I apply Snell's law at point P, what are we going to get? If you apply Snell's law at point P, what will we get? If I take the refractive index of this medium as mu1 and refractive index of glass medium as mu2. So apply Snell's law, mu1 into sin I is equal to mu2 into sin R. Accepted? Similarly, apply Snell's law at Q. What do we get? Applying Snell's law at Q. What do we get? I want you to tell me. Mu2 into sin R is equal to, completed, mu1 into sin E. Students, why is there no response? Are you guys able to understand or not? Did you understand how I wrote? Am I audible in the first place? Are you guys able to hear me? Why is there no response? So mu1 into sin A is equal to mu2 into sin R. Similarly, mu2 into sin R is equal to mu1 into sin E. So here it is mu2 sin R, which is equal to mu1 sin I. Here it is mu2 sin R, which is equal to mu1 sin E. So from 1 and 2, can I conclude that mu1 into sin I is equal to mu1 into sin E? So mu1 and mu1 will get cancelled, which implies sin I is equal to sin E. And from this, we can conclude that I is equal to E. So this is an important conclusion that we can draw, that when the angle of incidence is equal to angle of emergence, we can say that the emergent ray is parallel to the incident ray. This is what we will find using experiment also. Okay, but before we do the activity, let's try to understand the theoretical part. Okay, so emergent ray is parallel to the incident ray. Did you guys make a note of all these points?
Yes, sir.
Now listen to this carefully. This is the activity they are trying to talk about. So this is the activity which I explained, refraction of light through a rectangular glass slab. Okay, and this distance is there, right? You can observe that the incident ray and the emergent ray are parallel. The distance between the incident ray, the distance between the emergent ray and the extended incident ray is what is called as lateral displacement. Is what is called as the lateral displacement. Okay. So I have explained what is refractive index. Okay. So here in textbook, instead of mu, they have used N21. So N stands for refractive index. And if you write the 21, no, it is called as relative refractive index. See, if I write only mu, I call it as absolute refractive index. If I write mu21, we call it as relative refractive index. So relative means comparison. Okay. Next is, so certain refractive indices are given here. You need not memorize any of them. Okay. Just we'll try to answer this question before winding up the session. Okay. So there is a ray of light which is traveling in air, enters obliquely. Obliquely means hitting at certain angle into water. Does the light ray bend towards the normal or away from the normal? Why? Okay, for that. So what is the, so there is a boundary. Light is entering from air to water medium. Is it going to bend towards the normal or away from the normal is a question. So for that we need to know the refractive indices. Yeah, we need to know the refractive indices. No, how did you conclude towards the normal? So for air medium, it is 1.003. And for water medium, it is 1.33. So a light is entering from rarer to denser. So it bends. What you told is right. It bends.
Towards the normal.
That's right. And they asked why. Why? Because light is traveling from rarer to denser medium. Here, second. I hope I'm not fast, right? Everybody is able to write it down. Second, light enters from air to glass having a refractive index of 1.50. What is the speed of light in glass? The speed of light in vacuum is 3 × 10⁸ meters per second. So can I say refractive index of glass is equal to speed of light in vacuum divided by speed of light in a medium? So speed of light in vacuum is how much? 3 into 10 power 8 divided by the speed of light in medium is V. What is the refractive index given, guys? 1.50 or 1.5. So what will be the value of V? V 2 into 10 power 8 meter per second. Right? The speed of light in vacuum. So the speed of light in the glass is given as 2 into 10 power 8 meter per second. Next, third one. Find out from the table 10.3 the medium having highest optical density and find the medium with the lowest optical density. You guys tell, it's a very simple question. Which one is highest, highly denser in terms of optics? Wait, the charge on my pencil is over, just wait. So diamond has the highest and air has the least. Okay, next. You are given kerosene, turpentine, and water. In which of these does the light travel fastest? Kerosene, turpentine, and water. You tell me that. Water, kerosene, and turpentine. In which one will the light travel fastest? Again, why is no one speaking? Am I audible or not? Speed of light in water is the least. Sorry, refractive index of water is the least. Hence, the speed of light will be more in water. So water is the answer. So refractive index of diamond is 2.42. What is the meaning of this statement? So it is having the highest optical density. That's it. Okay. So after this, it's going to be refraction by spherical lenses, which we will see in the next class. There's something similar to mirror only. We'll see it in the next class. Any other doubts from today's class?
No, sir.
Okay. So you guys can leave now. There is no doubt. I'll see you all in the next class.
Yes, sir.
Thank you, sir. Thank you, sir.